right? So this was the model we had for that bandit approach with an optimizer. We're talking about supervised learning. We're trying to learn a model of the world and try to predict it better. And once we have a pretty good prediction, we take an action, we see what happens. But we didn't have anything here with states, right? And so this part about states that we were talking about last week kind of adds the component where we still have some model. So I don't like this picture. My picture has a model in it. That we're learning about, I guess in the agent's head, there's a model of how the world works and what will happen if we take a certain action in a certain state, what will be the next state, right? So in the agent's head, there's a model, and the model predicts basically, well, I would write it differently. It predicts these outputs, and it predicts what will happen next. Given the inputs that it has already, right? So if it was in a state, and if it took this action, then what would happen, right? And in the way we were talking about there, if you've got some parameters of this function theta, and you're trying to optimize them, that's the function you're trying to learn, right? But now the system's getting more complicated because we have states that we're keeping track of. We can move from one place to another. It's not just a randomized slot machine in a casino and you pull the arm and you win and you lose. It's okay, now you're at this stage of the game and you take an action and you still get no reward. And maybe you get no reward for a very long time or very weird rewards. And then the goal of the game, finding the treasure map or whatever, it gives you a very large reward, but you don't find it until later. So you have to do with little signals along the way and navigate your way through the space. That's the updated agent interface we have for Markov decision processes. Now we've added this state. And when we call it a Markov decision process, right, we've got this new words coming out of nowhere. Markov was a famous Russian mathematician who solved and invented a lot of things, especially related to physics and machine learning. The reason we're referring to him, and most people use his name on the front of everything, is that one thing he defined is this process for predicting state of a system over time, and he focused on systems where the knowledge you need is kind of limited in a very particular way. And I mean, he didn't call it a Markov chain or a Markovian property, but afterwards people did. And the main assumption is that if you're in a certain state of the system and you want to predict what's going to happen next, the only thing you need to know is what's going on in the current state. You don't need to remember what happened yesterday or 5 minutes ago or anything, because if you really have a true, full information about the current state, that's sufficient. And so when we talk about the Markov property or a Markov process or a Markov chain, it's all just a shorthand for saying, in this system, you don't need to remember 1 step back or 10 steps back or 100 steps back in order to predict the next step, because the state itself contains everything you need. Right? So in the real world, we assume that we need to remember what's going on and what time of day it is while we're walking around, or whether we have money in our pocket if we're going to the store. But you could think that, in terms of physics and really like reality, you don't, right? Like the universe doesn't care what happened 2 seconds ago. It only cares what's happening right now. And anything you think that might require information from the past, you could just say, well, that's actually still encoded in the present somewhere. It might just be very verbose or something. So it's not necessarily true about the world, especially given quantum physics, but I think it's still mostly true. But in reinforcement learning, we are going to assume it's true, because it does make things a lot easier. And it's a good approximation of the world. And it's not really limiting, because if you want to remember arbitrary things from the past, that would require an arbitrary memory capacity and functions, and it makes everything really complicated. And if there's anything you think you need to know, you could just say, well, that's part of the state, right? So, is your robot about to run out of power? Well, you could remember how long it's been since you charged, or you could just have access to the power level of your battery, right? Or an estimate of it. For the casino, you could have estimates of, you could say, well, how long has it been since someone's won on this machine? It's like, well, we could just have a count of how many times we've seen it pulled. Or you could literally have the time for various things since they've happened as part of your memory about the current state, right? So that means that everything is part of this state itself, right? And I guess the mathematical way to say it here is that if you have a probability, what's the probability of us getting some reward in the next state, which I was just saying in the previous slide here, right? We want to be able to predict the state and the reward at the next step if we're in this current state and we take this action, right? That's the way we're thinking of it. But in reality, this probability is composed of all the things that happened before to predict what happens next. And so when we make the Markov assumption, or we say something has the Markov property, then we're saying these two formulations are equivalent, that you can just drop all of these and it doesn't make any difference because they're irrelevant to the distribution, because this state contains everything that's required. Now it's an assumption, and so if you can prove that the system you have that you were dealing with requires memory of the past, first of all, I would argue with you because I almost believe it's almost never necessary, but it's technically possible, and it wouldn't be applicable to these types of systems. So Markov decision process is one where system where we're trying to make decisions over time. We have the Markov assumption, so the dynamics act like this. This is our dynamics function where we're trying to predict what's happening next in the world. This we didn't have in the bandits problem, right? Because we didn't have states, so we didn't have any dynamics about what happens next. Oh, I don't remember what's coming next, so I have to jump ahead, sorry. Right. So this is the real dynamics, is we're going to get a reward as well. I don't remember where we're going with this. Okay, let's just jump to the full one. In practice, what we're going to have, rather than having this one function probability over states and rewards as a single thing, we're going to have them separate, right? So we're going to say what state do you end up in next as a probability distribution, and then you're going to get a reward that was observed once you take that action in that state, right? And this we talked about earlier, having an expectation over the rewards, and this is what you're doing in the assignment. From the start state until now. And since it's an expectation, if you remember what an expectation is, right? It's a weighted sum over a series of events weighted by their probability of them occurring, right? And so this expectation comes out to be a sum over these probabilities of ending up in those state, any particular state with that reward, multiplied by the reward that you got. This form doesn't really get used in this direct way very much, but it's kind of a definition. So hopefully that makes sense. So like I said, it is true. This is more used in practice. So you'll see these forms more often. And it makes sense that they're more used this way because they're going to come at you separately, right? So you can have a simulator that tells you what happens next, or a video game, and you get the next state right away, and then you can act, and the reward will arrive as another signal that you'll kind of receive. So then what are we learning? In the bandit problem, we were learning a policy that just took an action, and you had to pick an action for each bandit, right? Now we're going to take an action in each state, right? So, I mean, you can make it as complicated as you want, but if you thought of the bandit problem where every row of the casino has 100 bandits in it, and that's one state, and then you first have to decide which row you're going to move to, and then you get to choose the bandit in there, right? So moving to which row of these machines would be like moving to state. But you don't even get to choose where to move. The world moves you there. But I mean, a more practical thing, just think about the robot moving around, and it's in one state of the world. It takes an action, and then it finds itself in another state, and it has to be able to take actions there too. So the long and the short of it is every the policy can be seen as a table like this, where we've got states as the rows and actions as the columns, and you're going to have probabilities or numbers here telling you how likely it is that you should take this action. However it's being defined, eventually this will be all just like a function that defines this probability distribution. But the important part is that every row of this table has a whole bunch of new parameters, right? So you could have a completely different set of actions, a different distribution for acting in every state, right? So the robot, as it's moving around, when it's in the middle of the room, it's just worried about how to move left and right, how to check its power indicator or something like that. But when it's near a door, is a whole new set of things. Like, oh, maybe I should move my arm and try to open the door, right? So the actions that are available in this state might be different, and the actions you could take might be different, right? So the robot could move its arm when it's standing in the middle of the room, but there's no point to do that. So maybe it's done it and tried it, realized it was pointless, and it just wasted power, and it stops doing it, right? But they're independent, right? So the actions you take in every state are independent. And we've talked about this before, right? So you're trying to still maximize your reward over time, your expected reward. But you're trying to basically learn this policy. Because our entire goal is to learn this policy in some way. And there's a couple major, like, different ways of doing it, depending on what information you have access to. So we've got our robot. This is going to be a recycling robot, so it's trying to decide it should go around, pick up garbage in the office, right, in the lab. And so one of the actions it can have is it can decide, it can wait for people to bring it garbage, and then it can throw it out. Or it can go back to its base to recharge, or, okay, good, it can go find garbage on its own. Be a lazy robot that's only taking garbage you give it. So you can hand it some recycling or some garbage, or it can just pick it up off the ground, or it can recharge. These are the only actions it has. These are very big actions, because go home to base is not a single action. It's like, okay, now run this path planning policy and go. But we could see these as 3 high-level actions. So we want it to actually, search. If it finds garbage on its own and throws it out, we're going to give it lots of reward. But if it runs out of power without recharging, it's going to get, negative reward, right? Because we don't want it to run out of power. And if it throws out garbage, when you hand it to it, fine, that's good. It's not saving us very much effort. And so some of the state it's going to have is this high-low energy signature, how much power it has left. And I guess maybe in this domain, we don't even have where it is. It was a very simple model of this. We say we're going to draw a state diagram now. You've probably seen these in control class or somewhere. Have people seen these diagrams before? The state diagram. So in this domain, the states we have are just high and low power, right? So is our battery high enough to continue, or should we go recharge? And then we're assuming that these other actions are like high-level processes, and when you decide to search, it does like some planning process that goes and does that. Actually, in all of these cases, it does. But we're just trying to make this decision here. And so what we're describing here then is all the possible things you could do, and you could define the entire state space and transition dynamics and actions that are available with a transition diagram like this, right? So you're in the states, which are circles, and the path, these lines, go through some action, right? So the actions are wait, recharge, or search. And then on the lines are labeled with the probability of that path occurring, right? Because after the action, that's why it's a 1. After the action occurs, then there'll be some split or bifurcation, however many possibilities there are. In this case, there's only 1 or 2 possibilities each. And so you've got the probability and you got the reward, right? Of that path happening. So, and so this tells you basically the entire description of the MDP. So an MDP could be very big, but you should be able to still draw a diagram like this of all the parts if it's fully described. Right, so when we search, we don't know if we're going to find anything, right? Actually, we don't even care about that in this system. We just know there's a beta probability of us staying in the same low power state or finding something. Recharge, you definitely recharge. Sorry to remind myself how this works. Alpha, your probability of searching and you still stay in high, but there's a 1 minus alpha probability that you'll switch to low, right? So if alpha is 90%, then every 10 steps, there's a good chance you'll switch to low power and need to go charge. Now what does beta mean again? Right, okay, so yeah, your reward is how many things you might find over that period. That's great. I'm just forgetting how we switch from low to high, because you might accidentally recharge while you're searching. That seems odd. This makes sense, right? Weight is deterministic, so you stay where you are. I have to go back and read the definition of it again. I guess there's a possibility that you, while you're searching for cans, you accidentally hit the recharge station and recharge. But that's how all the states can be described. Right, and so we're talking about talking about high level things so far, but they could be very low level actions as well. It could be about controlling the motor and the gear, rather than the very high level one for this example. And yeah, your agent could be a subsystem of the robot, which makes sense what I was talking about, that maybe when you take a certain action like search, you actually kick off a planning algorithm that does some other activity, so it doesn't have to be the entire thing. And so, yeah, this kind of model works for a lot of things. The reason it's harder in reinforcement learning, as this goes back to what we were talking about before, is that we don't know all these little numbers, right? So we're given the model where here's an MDP, and we might tell you what the highest rewards are, or maybe what the reward is for finding a can, but you don't know the distributions of it, you don't know the transition probabilities, and so you're trying to learn a policy where they give you the graph without the numbers on it. That's a nice way to talk about it. And can you learn these numbers and find your way to a high expected reward even if you don't learn all of them, while moving essentially through this graph. That's kind of a simple way to look at what we're trying to do here. And so the return, we talked about rewards, and you guys are looking at return in the assignment. Whatever action you take, you're going to get some reward, right? And so you'll get a reward at each time step. This is not like subject to state S or state A. This is the actual one that occurred, right? So now we've recorded a bunch of rewards you accrued over time as you move through that graph. And that's the record of what happened. And the total reward you get for this episode, an episode would be like one play of the game, or the robot moving and trying to learn through one duration until you stop it. And then we can do many episodes of training, but the total reward is going to be just basically all of those added together. But we can have different ways of optimizing that, right? We may want to optimize to maximize the total reward, so just basically get as much money as you can, regardless of how long it takes you, right? Because this has an assumption that all future reward is equal, right? How much do you want to get the reward at the end of the game, or the money in the casino, if it's going to take you like a year to get it? So there's other ways we could do that. We could have the rewards rolled out over time and say that the actual thing we're maximizing the expected return for the whole system, rather than just being the sum of the rewards we get. It could be the discounted sum, right? We could say, I want as much reward as possible, but I want it now, right? I want it sooner rather than later. And the further it is in the future, the less interested I am. So we discount future rewards. Or we could average the rewards that we get per time step, so that they're kind of more regular. So we talked about, I guess we should talk about these, yeah. So I mentioned episode. There's two kind of different tasks you could be doing in an MTP. You could be doing episodic task. So this fits best with like a game that you're playing, trying to get through a maze, or playing a video game where it ends, right? So when you get to the end, it's over and you stop, and then maybe you play again and you learn how to play this domain, right? And it's not necessarily, it could be that the reward comes all at the end in a single batch and you get nothing until you get there, or you get rewards along the way, and when it ends, you can look at your total reward, right? That's how video games work. But there will be a terminal state, so that when you get to a certain state, it will stop and then the game will end. But you could also have a continuing task where it never ends and you just keep going. So you have to stop at some point and learn. But essentially then when you're learning, you're only learning so many steps into the future, right? So say you're with a robot and it's a way to move around the environment and learn how you should control this robot. The world doesn't end, so a robot's tasks don't really end. You could say, well, we're always just training, let's train for 10 minutes of experience and see what we can train it to do. And you can keep training it for 10 minutes at a time, but you're always learning with that 10-minute horizon, right? And so you want it to be able to run forever, but it's really only ever thinking 10 minutes in the future because that's what its horizon is, right? And so we have some discount rate where we say the future isn't as important to us, because if I try to worry about all the things that are going to happen, 2 days from now, I'm not going to be able to get anything done today. That's definitely how it's all working during COVID here. So it's good to be able to say, you know what, stuff that's too far in the future, I don't have to worry about it. So I'm going to put a discount rate. And the discount rate we put is this gamma. So if you're in your LaTeX, it's the Greek letter gamma /gamma. I'll write it, it'll look like that. Much less neat than the font here. And it's going to be a number between 0 and 1. You can think of it, it's not really a probability, it's a discount rate. But basically, the closer it is to 1, the less discounting you have, right? Imagine if you're rolling it out like this. Here's your formula for it. If gamma equals 1, then it has no impact. You're just basically saying total reward, right? So gamma equals 1 means that you're using the total reward. And gamma less than 1, it's this discounted reward. And that's important. Most of the time we're talking about discounted reward, because most of the time you want to say, I really want to get immediate reward here, maybe in the next couple steps, but I'll worry about, step 3 when I get there, right? Because when you're at step 3, it won't be gamma squared, it'll be no gamma. It'll be gamma 1, because gamma, this is gamma 0, this is gamma 1, right? So gamma to the 0 gives you 1, so it's basically not there. Gamma to the 1 gives you gamma. And if gamma is 0.9, then the reward here, even if you get the same amount of money, same amount of reward as you got in the first step, it's only going to be 0.9 of that, right? And then in this step, it's going to be 0.81 of that, and it's going to get smaller and smaller very quickly. So it's a standard way. This is a core thing that'll show up everywhere in reinforcement learning discount rate. And it lets us focus on not obsessing too much about the perfect future. So an example of that here. Oops. Oh, sorry. an example of that with a simple task, a pole balancing task, which you probably done in control classes. You have some kind of simple device where you can move. In this case, you've got a car, a little motorized thing that you can move backward and forward, and you can control the power going to this, so how quickly it goes, and the goal is to make this stand directly up so it doesn't fall over. And you get negative rewards whenever it goes away from standing straight up, and a lot of negative reward if it falls down, right? So you can optimize this quite directly, and since you can put in the physics of the system and then get a feedback, you can do this almost perfectly because it's simple enough. But you can also do it as reinforcement learning. I guess the idea of this one is if episodic, then you just give it reward all the time so that it's getting something along the way. And so it's trying to stay up as long as possible. So in this case, you give it +1 if it hasn't fallen over, right? And so it tries to stay up as long as it can. But eventually it'll fall down, and you consider that the end of the episode. So the time length of episode isn't necessarily fixed, right? That's kind of a point. It could be episodic because you know it's going to end. Eventually it's going to fall over, but it's not that it's like 10 steps. It's until it falls over. And if you wanted to set it up as a continuing task, you could give it -1 whenever it falls and just say, well, as long as it hasn't fallen, I'll give you 0. But then you discount it and say, I'm not worried so much about infinitely far in the future, just worry about it not falling down right now, right? And so it'd really be aiming for 0 here and not getting any negatives. That's kind of one way you can do that. And so often when you do an episodic test, especially if it's not a super long one, you might have no discounting, right? Because you actually want to have it consider all the steps equally. But even if it's a very long episode, you might still want to have discounting. Another example here is the mountain car. Here you're trying to control a car to get to the top of the hill and not fall over it and come back down. It's another very classic original problems. And so in this one, the same thing, you give it a -1. One way to set it up is give it a -1 as long as it's basically not gone over the edge, right? So as long as it hasn't gone over the edge, that's great. Or no, you're trying to get it to the top, right? Sorry, not the top of the hill. So it has a -1 until it actually hits here, right? And so once it gets here, it'll stop getting -1. So it's really trying to get up there as quickly as possible because it keeps losing money as it's going up and down here. And so your return then, without any discounting, is just how many steps it took you to get to the top of the hill. Because as long as you keep going up and down, it's going to be that, and then the episode ends when you reach here. And so it's good because by setting up this set of reward, you're setting it up so that the thing you're trying to maximize, which is get to the top of the hill as quickly as possible, is reflected in the reward. So it's a good idea to try and have your rewards set up in a way that if the agent learns to minimize your reward, it's probably going to be solving the problem efficiently, right? If you put a reward in that's kind of meaningful to you metaphorically, but doesn't relate to what the robot has to do or what the agent has to do, it might actually be a bad reward function. So you could set up an MDP where the problem is very solvable and understandable, but the reward function is weird and it's hard to solve because you're leading it. The rewards lead it from one step to the next, right? And so you may not know how to solve it as an entire policy, but the way you choose the reward has an impact on how efficient it is going to be to solve it. Okay, some more notation on this stuff. We're going to have episodes starting from this time step 0. So state 0, time 1. Yeah, and we're not going to distinguish between episodes, right? So you're learning about some generic episode, and maybe you'll train for thousands of episodes, But what you're training about is how to learn what the agent's doing every time it starts from state 0 and then learns for a while, right? So you could be doing this many thousands of times, but you're trying to learn how to play this MTP, how to move through the state diagram, given the start state. Yeah, and then the return you're talking about in general is just going to be represented by this function because you've got the discounted factor, which is how many steps in the future from that particular state you're at. And then the reward for that time step forward given how many steps you are ahead, right? So when we're at the start state, we're saying what's the return we get? It's the return we get for all the steps going to the future where we discount how much they are important to us and we add them all together. So it's just a mathematical representation of that. But it's true for every state, right? So when you're in the first state, right, we're going to have the G1 return. You could say what's the return for being here and having that going forward. That's what we were talking about at the very beginning of the assignment. How do you evaluate that? And these returns are going to be critical because the thing that you're learning is to basically model these and then decide what you should do next, right? And the stuff that happens in the next chapter next week is that there's a lot of repetition here, right? So I mean, obviously, these calculations here are equivalent, so there's no need to compute them twice, right? So the computation for G1 is included inside G0, and so that's why dynamic programming is going to be very useful because you basically want to do all this, compute these numbers, but without ever duplicating calculations. Okay. And so I think the next lecture on YouTube actually goes on from here. It's kind of where it starts. So you start saying, actually I have an example. If you have the return for a particular system, and we've given you the actions to maximize, we give you a series of returns. So if this is the actual reward sequence that you got every time step, and the discount factor, then what's the return you would actually get by following it forward, right? And so yeah, I think this is where we start on YouTube after this. So I will leave it there. Does anybody have questions? Okay, if not, I'm going to wrap up. Thanks for questions you guys had, and since I recorded that, I will create a new version and put that up, more summarized view for people. Hopefully this part's not too complicated, so people are able to read up on it if they were missing that video, but we'll put this up there too. So talk to you online, and thanks for coming. Bye for now.